Hi everyone and welcome to this new video about three-phase power circuits. This is our example number 3. In this example we will consider a different system. In this case we have a delta connected source and we have a Y connected load. So we have a delta Y system as shown here. So what is given for this example? We have the following data is given for the delta Y system operating at 50 Hz. Okay, the phase voltages are the following. So we have VA is 400 phase 0 degrees in volts. Exact same amplitude for VB and VC with the orientation are 120 degrees and minus 120 degrees. So we have 0, 120 and minus 120 degrees. The loads are all the same. ZA is equal to ZB is equal to ZC. And there's a series connection of the resistor and a capacitor. And this is the reactance of the capacitor. And the values of the resistor and the capacitor are shown here. So 30 ohms for the resistor and 127 millifarads for the capacitor. Alright, and so we have a couple of questions. The line voltages, that's question A, and the load voltages, or line voltage are actually between these points, these nodes, and from that point to that point all the way. So it's actually shown here, VL1, VL2 and VL3. We need to calculate the load voltages, so the voltage drop across each load. We need to calculate the current of the load, so load currents, so the current flowing through each load. And we need to also calculate the line currents, so the current actually flowing in this line. So 3 IL1, IL2, IL3. And we need to calculate the phase currents. And the phase currents is, as we discussed in the previous two examples, these are the currents supplied by each phase voltage. So we have here I phase of C and I phase of B and I phase of A. So we will consider that in the final stage of this analysis. So let's first, as we did also in the previous examples, let's first determine the expression for the load, because we have a value for the capacitor and the resistor. We don't have the value for the impedances. And we need that in a polar representation such that we can carry out the rest of the calculation. So let's first start with the load. So loads, in this case it is ZA is equal to ZB and it's also equal to Z of C, which is a series combination of R and the capacitor, so R and the minus J of X of C. So what is X of C? X of C is equal to 1 over omega divided by the capacitor value C. And omega is 2 pi times the frequency, so we have 2 pi times 50 times 0.127. These are all given. And if you calculate this, you will get very close to 40 ohms. Then, if you substitute the values for the resistor and the determined value for X of C, in this expression you will have Z of A, Z of B and Z of C. All of them, of course, will be the following expression: 30 minus J, 40 ohms. And if you convert this, which is the required expression for the further calculations, will be in the polar notation, will be 50 phase minus 53 degrees. And the conversion of the rectangular from the rectangular expression to the polar expression, we have discussed this in great detail in the other videos and also in the separate video about complex numbers and phasors. So I will suggest you to look at this. Okay, that's for the step 1. Now we will consider the first question, so line currents. I mean line voltages, excuse me, line voltages. So let's first do that. What are they? Line voltages. Now, as we discussed in the previous examples also, we have to determine what the orientation is in this circuit. So we have the VL1. How do we determine VL1? So VL1, which is actually this voltage from this point all the way to that point. So actually you're going with in the clockwise direction, so you're actually turning in this form. It means actually from point A to point C, but this is just exactly the voltage VA. So VA, which is given already in the equation, is just VL1. So line voltage 1 is in this case VA, which is 400 volts with a phase orientation of 0 degrees. Now let's do other two. So VL2, which is again in the clockwise direction. So you have this voltage, line voltage, which is again in the clockwise direction from point B to point A. That means just voltage V of B, which is also given 400 volts and 120 degrees in phase orientation. So you will have 400 phase 120 degrees in volts. And the last one, which is VL3, if you look again in the clockwise direction, it will be from point C to point B, which is this length of the VL3, which is exactly the same as VC. So in this configuration for the delta connected source, the line voltages are equal to the phase voltages. So that's actually also very important to note. So let me write it down also, and also here, because I better also denoted this as VB, which is 400 phase 120 degrees in volts, and this is V of C, which is 400 volts in minus 120 volts. So these are the three unknowns for question A. So that's actually very easy. Let's look at question B, the second one. The load voltages, we have to calculate the load voltages, or actually the voltage across each load. That's actually a little bit difficult, and we have to make a very precise definition in this case for this configuration and also for this sequence. We have the following expression for the load voltages, and I will check that afterwards to verify our formula. So load voltages. Okay, so what we have is the following: the V of ZA, which is the voltage across the impedance ZA, will be the phase voltage of A, which is just VA, of course, divided by the square root of 3, and now comes the formula. The phase will be the total phase will be the phase of the source of A, the phase of VA, minus 30 degrees. So what do I mean by that? This one is just the amplitude of VA, so that's just 400. And this one is the phase of VA, that's just 0 degrees in this case. So what you have is the following. You have 400, you divide by the square root of 3, and then phase 0 degrees minus 30 degrees. And if you just simplify this, you will get 400 divided by the square root of 3, phase minus 30 degrees. And you have now the voltage across the impedance ZA. I will verify this, of course. I will first calculate the other two, and then I will make a check that the voltage, these expressions are indeed correct. So let's move on to V of ZB. So that's actually again the phase voltage for B divided by the square root of 3, and then the phase orientation of the voltage VB minus again the same constant 30 degrees. And what you have is 400 divided by the square root of 3, and then phase, which is 120 for VB, which is shown here. Again, same amplitude, 400, and then minus 30 degrees. And if you simplify this, you will get 400 divided by square root of 3 and phase plus 90 degrees volt. Alright, so these are the two unknowns we have determined. Now the last one, which is the VZ of C, which is the phase voltage of voltage C divided by the square root of 3, and the phase is done the theta of C, which is the phase orientation of the voltage V of C, minus again the constant, the 30 degrees, and then you will have the amplitude, which is 400 again for V of C divided by the square root of 3. This was for the theta of C was minus 120, so minus 120 minus 30 degrees, which will result in 400 divided by square root of 3 phase of minus 150 in volts. Okay, now you might ask, okay, how can you show that this is correct? Again, these formulas using the minus 30 degrees for the load voltages from the phase voltages and the phase orientation from the phase voltages is only valid for this configuration and for this sequence. So you have a different sequence, can be a plus 30 degrees or different value. So be careful if you follow other examples. So what I want to do is I will do a check. So I will have the following. I will check. Okay, what do I want to check? I will check the following. This voltage, VA, if you just apply the Kirchhoff voltage law here, from this point B to A must be also this voltage plus this voltage, which is of course VZB minus, because there is a minus here, VZA. You can also say that, right? That's actually what it is. You can also say the same thing for this. From this point to that point, from point A to point C, that will mean actually this voltage from the ZA minus the voltage across ZC. So let's do the second one, just check this. So if this voltage minus this voltage, if this is the VA, which is 400 volts and with a phase orientation of 0 degrees, then we are actually correct. So let's do that. So I will do the following. I will say V of A is that equal to V of ZA minus V of Z of C. Again, look at it in the, I will zoom out a little bit. So this point to that point is exactly the same as from this point, because this is just one connection. So from this point to that point is from this point to that point. That means actually this voltage, VZ of A minus VZ of C. And I already calculated these two using, of course, the formula, which is just a formula. So I will now verify that the formula is correct. Okay, now let's move on. So let's substitute everything in this expression. So I will continue with maybe just blue. So what we have is the following. The left side is just 400 phase 0 degrees. I will check that, of course. It's just still a question mark. What do I have for VZ of A? It's just this, 400 divided by square root of 3, and a phase of minus 30 degrees, minus the same amplitude, 400 divided by square root of 3, and it will be a phase orientation of minus 150 degrees. 150. Now, we can, of course, use the formulas for converting the polar notation to the rectangular notation, because we want to add or subtract. It doesn't matter, the same principle with a minus sign. So I will do it also step by step, just to illustrate the formula. So what do we have? We have the 400 divided by square root of 3, and I will take in the brackets the cosine of the angle, which is minus 30 degrees, plus j sine of the minus 30 degrees, again same phase. For the first part, that's done. For the second part, we have again the amplitude outside the bracket, so we'll have the cosine of the minus 150 degrees plus j sine minus 150 degrees. Alright, so if you now calculate the values for the cosines and for the sines, all those expressions, what you have in exact form for this, for the first one, is square root of 3 divided by 2. The other one, the sine expression, will be minus j a half, so 0.5 j. Now, this is for the first one. The second part will result in minus square root of 3 divided by 2, and the other one will result in minus j half. Okay, that's actually for this. If I now combine the real parts and imaginary parts, what do I see here? I see here square root of 3 divided by 2, and I see here plus and minus, minus and a minus will be a plus. So again, the same expression, so I will have an additional square root of 3 divided by 2, so I will have in total a real part of square root of 3, So you have the following: 400 divided by square root of 3, and additional from this real part plus this real part, using the minus sign here, I will have in total net square root of 3 as a real part. Now this is minus j 0.5 or half, and it is plus, so these will cancel each other out. So I will have 0 imaginary part, and that's very interesting because now this pure real expression. So what do we have is the following: I will now calculate the magnitude of this and the phase. Yeah, the magnitude of this is of course this one only because there is no imaginary part, and the phase of this is just 0. Okay, so that we have the following. So 400 divided by square root of 3. I will just follow exactly the same formula, just to illustrate the thing. This is of course overkill, but to let you know what's actually happening. So we will take also the arctangent of the imaginary part divided by the real part. Sometimes helpful to do that in a little bit slow pace. So what we have is the following: this will be 400 divided by square root of 3 times, and this one is just square root of 3 in total with the square root, etc. So you have all times square root of 3, and this will be phase of 0 degrees. You can calculate it by yourself. So you will have, now what do you see? Square root of 3 divided by square root of 3, so those cancel each other out, and I'm left with 400 phase 0 degrees. And interesting, this is exactly the same expression for VA. So I have VA is equal to VZA minus VZ of C, and I have used these formulas. Of course, just came out of nothing. So you might ask, why is this correct? If you haven't made a check, there's one expression and it is actually valid. So you can do the same check for the other ones, and you will have again the correct answer for each of the phase voltages. Okay, that's just about the check. So let's continue with the calculation of the load currents. Now this is actually also very easy because we already know the load voltages, each of them. Now using Ohm's law, we can say the load currents are load voltages divided by the impedance. So I will do that in the next part. So the load currents, and using Ohm's law, we are actually very close to that. So it will be IZ of A will be VZ of A divided by Z of A. That's actually the expression for the load current. So what is the expression for VZ of A? It was 400 divided by square root of 3. Phase was minus 30 degrees. And divided by 50, phase minus 53 degrees. And if you now do the math correctly, so you divide by the amplitude, so this one divided by that one, so amplitude here divided by the amplitude there, and you subtract the phases, so you do minus 30 degrees minus 53 degrees, so you will have 8 divided by square root of 3 phase 23, and this will be of course in amperes. Okay, and I will move on with the next one, which is IZ of B, which is VZ of B divided by Z of B. Of course, ZA and ZB and ZC are all exactly the same. So again, I can write down exactly the same expression for the impedance, but the voltage amplitude is the same, but the phase orientation must be 143 degrees. And if you again do the math, you will get exactly the same amplitude for the current, but the phase, this is 90 degrees, excuse me, this one. Okay, then you will get 143 degrees for the IZ of B. I will do the IZ of C here. So IZ of C, which is VZ of C divided by the impedance ZC, which is 400 divided by square root of 3 phase of minus 150. So what you get is divided by 50 minus 50 degrees, and you will have exactly the same expression for the amplitude, and the phase will be minus 87, and this will be of course also in amperes. I mean 97, excuse me, this one will be 97. So let me correct this. So this will be 97 degrees in amps. Okay, that's actually for the three currents. These are the load currents. So we have this, the exact same expression for the amplitudes, but the phases will be again plus 120 degrees. This also plus 120 degrees, just addition of 330 degrees, 360 degrees I mean, and you will have the expression shown here. Alright, so let's move on with the next question, which is question D. I will a little bit zoom out. Which is the line, which are the line currents. Again, we have there also a formula, as we did for the load voltages, so the line currents. So what is the formula? And again, for this configuration, line currents. So let's move on with the line currents. I mean for the phase currents. For line currents is very simple. So line currents, let's do that first. Line currents, what are the line currents? IL1, IL2 and IL3. These are the line currents as shown here. So we have the IL1, let me a little bit zoom in, IL1, IL2 and IL3. And you can already see this is actually the same expression for the IZ of A. So exactly the same expression. So if you know the IZ of A, yes, we know because we already calculated it in the part C. So we can also actually equate it to each other. Again, IL2 is equal to IZ of B. IL3 will be equal to IZ of C. And I will just write them from the expressions we have calculated actually in part C. So what we have is the following. Let me continue with black. IL1, which is just equal to IZ of A, which is just this. And I have also the other one, which is IL2, which is IZ of B, again 8 divided by square root of 3 and phase of 143 degrees. And the last one, I will make it here. So IL3 will be IZ of C, which is 8 divided by square root of 3 phase of minus 97 degrees in amperes. Alright, that's actually for this, and we are done actually with the line currents. The last one is for the phase currents. This is actually a little bit complicated, so again we have to use a formula and we will again check that. So for the phase currents. Okay, the phase currents, so I will make this with I phase of A, which is the current through the load, IZ of A, divided by the square root of 3, and what you do is actually the following. You take the phase, which actually have determined for the load ZA, that is 23, and you add, in this case, 30 degrees. So if you do the math, you will have 8 divided by square root of 3, just for the amplitude, divided by again the square root of 3, and the phase will be 53 in total. And this will be 8 divided by 3, phase 53 degrees, and we have amperes. So this is exactly opposite of the formula for the load voltages. So remember, we had minus 30 degrees and we have now the plus. I will again check this. I will make a check. So I will do the other two also for the phase current for B. Let's also define where it's actually the phase current. We have already defined this also in other two examples. So let me draw this in the circuit. What I mean by phase current is the following. This current flowing in the branch of VA is I phase of A. And this current, which is going here in this direction for VB, is I phase of B. And this current for the VC will be I phase of C. Okay, that's actually for the phase current. So I will move again all the way down. And continue again using the exact same expression for the current, for the phase current. So what do I have? I have let me continue with black, IZ of B divided by, again, just a constant, square root of 3, and then take the phase for the IZ of B, which is shown here, 143, and add again the constant of 30 degrees. And again, if you just substitute everything, will be 8 divided by 3, and the phase will be 173 degrees. And this is just for the second one. And I will now do the final one, which is the IP of C, which is IZ of C divided by the square root of 3 again. And the phase, which was minus 97, which is shown here, 97, so which is minus 97 plus again 30 degrees. What do we have? Again, the same amplitude, and this will be phase minus 67. Now we have calculated all of the phase currents, and actually the whole example with the questions is completed, but I will make a check because I would like to check that these are indeed the correct formulas to calculate the phase voltages. So how can I make the check? Now I can do the following. Let me write it down. Check. I know the following. If you look at the circuit again, just move up a little bit, zoom in. I know all the phase currents now. Now if this is indeed the phase currents I've calculated in the last part of this analysis, then I will have the following. The IL1, which is a line current, must be, this one must be equal to IP of A minus IP of B, just Kirchhoff current law at the point A. So this, I can check that. If this is correct, then I can say, okay, the phase voltages here are correct. And you can do the exactly the same check for point B and point C, so that you can verify the formula. So what I want to do is the following. IL1, is that equal to IPA minus IPB? Okay, so we will move again to the analysis all the way down for the check part. So what I said is the following. Is IL1, is that, question mark, is that equal to I phase of A minus I phase of B? Now what did I have? I had for IL1, which is shown here, I had 8 divided by the square root of 3. So let me make it more readable here. So this was square root of 3, and phase phase of 23. So I have the following: 8 divided by square root of 3, phase 23 degrees. Is this equal to the IPA, which is shown here, or here, plus, minus this? Is this correct? Let me check. So actually what I want is the following: 8 divided by 3, phase 53 degrees, minus 8 divided by 3, phase 173 degrees. Again, we do the same analysis. We go from the polar expression to the rectangular orientation, or form such that we can do the subtraction here. So I will do the same procedure, 8 divided by 3, brackets, cosine 53 degrees plus j sine 53 degrees. That's for the first part. Again, minus 8 divided by 3. You will take the cosine of 173 degrees plus j sine 173 degrees, and it's actually the final one. So let's write it down. 8 divided by 3, which is cosine of 53 degrees. If you had the exact expression for this phase, it must be 53.13, but anyways, it was, and you will get, if you do the math, you will get exactly 0.6 or very close to 0.6 if you have rounded off. And for the sine part, you will have j 0.8 plus. Now, the second part, you will have for cosine of 173 degrees, you will have minus 0.9927. I will just make it a little bit accurate. And for sine part, I will have j 0.1196. Again, I will have to combine the real part and imaginary part, make an effect, net effect of that. So I have here 0.6, I have here minus minus, so I have a plus 0.9925. And that will result in, for the real part together, will be 1.5927. And let's look at the imaginary part. We have 0.8 minus 0.1196. That will result in minus 0. Plus, still plus 0.6804, and that's actually for the expression, still in the rectangular expression. So I will need to express this in the polar notation, and I will check if this is the result from this. So let's move on. So what I want to do is 8 divided by 3, just the amplitude, and I will make the square root of the square of this plus square of that. So that's actually the known formula for the length of the vector. So I will have the following: square of that plus 0.6804, and I will do the tangent of arc tangent, of 0.6804 divided by 1.5925. Now let's calculate this. This is 8 divided by 3. And if you do the math very carefully and very exact form, you will get the exactly square root of 3. This will be square root of 3. So this one will result in square root of 3. So I will have square root of 3, and this phase, the arctangent of this expression, will be 23 degrees. So what you have is the following: 8 divided by 3 times square root of 3 will result in this. And if you simplify this expression, you will have 8 divided by the square root of 3, and the phase is exactly the same. And look at it, you have exactly the same expression for the current, for using the subtraction here, and you have the line current IL also produced. So we made a check such that we can verify that this formula also is correct. So remember, in this example, we have used a specific configuration for the delta source, and that will allow us to use the formulas for the load currents and the load voltages we have used in this example. So be careful, don't use this just blindly. Look at your configuration for your source and then decide if you can use it or have to make an addition using a minus sign for the load voltage and also for the load currents. Okay, thank you very much. It was for the example number 3. Again, a little bit lengthy example because we would like to verify a lot of stuff in this, but it will give you a lot of background, and we will not haste in this actually very important example. I will see you in the next example, in example number 4, about a different configuration for delta delta. That's actually our final example. So see you next time and take care. Don't forget to share and like. and have a nice day.